Okay, good afternoon, everyone. It is a great pleasure for me to introduce for us our visitor, whose name is pronounced, as he said it, Lukasz Wyrzykowski. And all those years I was pronouncing his first name wrong. It was just Lukasz.
That's close enough.
Close enough. Lukasz, he's going to be with us for 2 more weeks. And he is currently a professor at the University of Warsaw. He did his studies there. He obtained his PhD there some time ago, and then he moved to a warmer climate. He went to Tel Aviv University for a year, and he thought it was too warm, so he went up to sort of like cold and wet, went to England, spent a year at Manchester, and then 10 more years at the University of Cambridge, where he, I presume, was involved with the Gaia mission he's going to talk to us a bit about today. And then he came back, as many do, to his homeland and as a professor at the University of Warsaw. And he's a world expert, actually, in all things related to time domain astronomy, how to process big data, how to coordinate small telescopes. And one of his leading role in various large European projects is actually the coordination of nearly 100 small telescopes in Europe and all over the world, and how one could use them efficiently in order to actually do novel science in time domain. And some of the exciting results he's going to talk to us about come from observation along those lines.
Okay. Thank you very much, Vasilis. Thank you for the invitation. Thank you for hosting me. As Vasilis said, I'm here for 2 and a bit weeks organizing some conferences, workshops, but I'll be around, so I'm happy to meet with people and discuss. Right, so I'll begin with the introduction, I hope it works, of the people involved, right? Because you don't do things alone these days. And this is a group of people associated with the Warsaw University Astronomical Observatory, but also reaching outside. You see some of them carry Gaia logos. Some people are involved in the Gaia mission, in the core of the Gaia mission. So we do the Gaia data processing. Some of these people have the logos of the ORP program, which is a time domain program sponsored by the European Commission. And then there are some people, there are also other institutes we collaborate with around the world. And I star, this is not working very well. I star some people, first Nada Ihanec, who is already here. She's my PhD student, working on time domain on quasars, but also start some other people who are going to be here next week or the week after. So a large fraction of people I work with are actually coming here. Actually, we enjoy, it's the second time we're actually organizing the workshop here because we like it here so much, the weather, the food, the sea, and everything. So there will be opportunities to talk with other people as well. Okay, so the outline of this talk today has actually 3 major parts, and they're kind of described in this very picture. So first, I'll start with black holes and what do we know and how to find them. And then I'll talk about surveys, especially surveys like OGLE, the Polish survey, then Gaia, the European mission, and then LSST, the large synoptic sky telescope. So I will talk about results and non-detection results as well, and then mention some challenges related to these. And then the third part will be about the black hole TOM. So we see the name black hole appearing everywhere. It's to catch your attention. So this is about the global network of telescopes for time domain astronomy. So they are depicted down there. Okay, so let's begin with black holes. This is the Astronomy 101, so I just want to do it extremely simple and quickly. And of course, as people involved in this kind of research, they know this is a very, very crude picture. But it is at least what we roughly understand. So the stellar evolution, it starts with a stellar cloud with protostars, essentially a cloud of gas, and then depending on the mass of that collapsing cloud, you either end up with small stars like our sun, or intermediate mass stars, or very massive stars. Of course, you can imagine the function goes that there is way more these low mass stars than the massive ones. And then, depending on the composition, the size and mass, they evolve, they produce more rich elements inside, and then especially we're interested in the onion ones at the bottom here, where you reach to the iron core in the middle, which then collapses into the collapse of the core and produces a supernova, which then yields either a neutron star if there is enough mass to constrain the collapse, or a black hole. And typically, very roughly, we say that everything dark, a product of supernova more massive than 5 solar masses, is a black hole, right? And of course, this picture, as I said, this is a very simplified version, and not every massive star produces a black hole. Not every black hole is produced from massive stars. But this is just to keep everyone on the same page. This is what we think we understand, but still there is many questions. So my point here is that by studying the end products, especially black holes, but also neutron stars and white dwarfs, we can verify these theories backwards, and we can learn about stellar evolution, which is kind of the basic of our knowledge. Everything is related to that. Every kind of research, even if you do galactic research or extragalactic research, this is something that we have to understand. New picture of black hole environment actually comes from gravitational waves. This is very recent, and it actually boosted the excitement about black holes again. And so here we see an artist's impression of two black holes colliding. So first of all, it must have been a binary system of stars, probably, evolving in a tight evolution, and then something must have forced them to get together after they turn into black holes. And then in the end, what we observe this final milliseconds of two black holes colliding together and emitting these gravitational waves, which we now are able to detect. Of course, you get Nobel Prizes for things like this. But for me, what was interesting here, and for many other people as well, is that the black holes detected by gravitational waves, they tend to be very massive, right? So this is, for example, an 80 solar mass black hole. So imagine the products. What must have been at the very beginning to create such massive black hole. So that's one of the intriguing aspects of this. I'll get to that in a second again. But before gravitational waves, we've been seeing black holes in systems like this. This is again an artist's impression of Cygnus X1. The name actually reveals that this is actually an X-ray source, where you see the very hot emission coming from the very center of there, where there is a lot of friction, and the friction emits force makes this object to shine in X-rays, and then additional observations revealed that there is actually some period. There is it's a binary system where you have a massive star which is close enough to have the matter accreted in form of an accretion disk, and also there's jet coming and so on. So you can find these kind of black holes, neutron stars as well, in very tight systems where there is an interaction between the star and the black hole. And this used to be the most massive black hole known in our galaxy, a galaxy of mass of 21 solar masses, of kind of stellar origin, and I'm not mentioning about the supermassive black holes in the very center, of course. So here you need a star and a black hole in a tight system, and people call them electromagnetic black holes. Right. Fairly new way of discovering black holes actually comes also from binary systems. And again, here you have a star, which is visible, and there is an invisible object next to it, but there is no accretion going on, right? So there is no X-ray emission, there is no gravitational wave emission at all. But what you see here, you can detect the black hole indirectly, again, by studying the motion of the star. So this is, again, another artist's impression of how it looks, more or less, and there has been a handful of examples of these systems being discovered in our galaxy, and here we now reaching to the most challenging black holes to find. So this is a real picture, this is the real data, and this is a non-interacting black hole. It could be single, it could be binary, but it has 7 solar masses, and prove me wrong. So this is what we are after, actually. Most of the black holes in our galaxy should look like this, right? How do you find them, right? So you have no gravitational waves, you have no X-ray emission, you have no star next to it, which can reveal the presence of the black hole. So this is where where the challenge is. Moreover, this challenge is connected to that challenge. Dark matter looks the same, right? So why not think maybe at least some of the dark matter is embedded in these compact objects, right? So that's one of the theories from back in the 1980s already, but this hypothesis is still present in a way. I'll get to that in a second as well. So to put it in one graph, people working in gravitational waves must have seen this picture many times. So here this is kind of like a quasi-histogram. You see you have the mass in quasi-logarithmic scale here, and the x-axis doesn't mean anything. So here you have in blue, you have all the gravitational wave detections. So you see two components then merging into one. And these days, the most massive one found was about, the end product was about 150 solar masses. And then you have the whole range. Most of them are actually within 80 solar masses or so. There were also some smaller ones, and here actually there were neutron stars merging with black holes, or neutron star mergers as well. So you see this is one side of the picture, of this butterfly, let's say. And then this is contrasted with this upside down butterfly, where we have electromagnetic black holes and neutron stars. So these are solely the X-ray binaries found up to date. So you see, first of all, that these two populations, they do not overlap, right? There's hardly any overlap, a very small overlap around here. So definitely there is something fishy going on here, right? So there is many things we don't understand yet. And of course, there are some questions you can ask here. People were asking about the mass gap. So the gap here you see between, say, 2 solar masses and 5 solar masses. In X-ray binaries, people were seeing a lot of neutron stars, and then nothing, and then black holes with masses about 5 solar masses. So they used to call it a mass gap, and people doing theory, they were scratching their heads, how do you produce a mass gap? Of course, people doing theory, they can come up with solutions, so they were able to reproduce that. But the question is whether it is an observational bias or there is something wrong with our physics. The other question is how on earth you produce such a massive black holes, right? Like we see in gravitational waves. Maybe it's the dark matter there. So at least these two questions you can immediately start asking while seeing this picture. But as I said, this picture is not complete, and there are other methods. So we're now trying to complement this picture. And let's start with the green dots here. So these are the electromagnetic non-interacting systems. There are some references here if you're interested. Actually, so far, I can only assure you about 4 confirmed systems, although there were probably furthermore examples produced in the literature, but then they were rejected. So the most massive one there, I'm going to spend 2 slides on, because it's a fairly recent discovery, also because this is the most massive one found so far. It actually exceeds the mass of 21, the previous record holder. So this is the system. As you saw in the previous animation, this is the star. It's a giant star with a low mass, about 0.7 solar masses, and it's in orbit around something fairly massive. So the mass of that black hole was measured of 33 solar masses. So this is at this moment the most massive stellar mass black hole in our galaxy. Also, it's one of the nearest. It's not the nearest, but it's like second nearest black hole to us. So it's only half kiloparsec away. What is also interesting about this is that it's on a crazy orbit. It's not in the galactic plane. It's actually on a halo orbit, which is actually retrograde, extremely crazy orbit, and it has very low metallicity. So probably this black hole came to our galaxy together with some minor merger, with a merging of another smaller galaxy with a much lower metallicity. So because we see some There are some structures in the halo called sequoia or ED2, which have the same properties, orbital and metallicity properties. So we think we can attribute that black hole, that system, to that stellar stream. So this is very interesting. So this black hole came to us and visited us, but we can now find these things, and this is what Gaia can do. You see, this is Gaia pH-free, so Gaia has already 3 black holes found with that method. One more plot to show here that these are the 3 black holes found by Gaia, and they coincide with the peaks of the distribution of masses seen in gravitational waves. So there is this first peak around something like 7 or 10 solar masses. There's another peak around 33 solar masses. So we found black holes from these 2 peaks, which is quite encouraging, is that we're now starting to merge these two populations together. Okay, now let's move to another method, which is shown here in red. So you see some examples there, and this is where my personal interests come in, and this is what we call microlensing. So microlensing, just to give you a very quick introduction to it, it's the consequence of Einstein's theory of relativity, where the space-time is curved, and any object placed in that space-time causes the curvature. Then if there are any light rays coming from the background, here I plotted a star, which is our source of light. It could be a quasar, it could be anything. Then the light rays are being bent by the presence of this object. So this could be a black hole, a planet, a star. It has to be compact enough to do the lensing. And then what we see temporarily, because in our galaxy everything moves relatively to each other, then we can temporarily see something going on with that background source. So this is what is called microlensing, and this is what Polish astronomer working in Princeton, Bogdan Paczyński, came up with in 1986. He proposed that we can observe millions of stars to see a couple of them behaving in weird shape, weirdly due to lensing by some objects in front. So we are here, this is the lens, this is the source. So microlensing is very rare. It's essentially 1 in a million stars is lensed. This is just, space is empty, so there is not much going on in the galaxy. So we have 2 flavors of microlensing. So first one is the star. This is what we observe, the star brightness. Star brightness is getting brighter during the transition. This is the Einstein ring, this is the source. So we see these 2 images, and because we see these 2 images, we cannot separate them. Then the total brightness of the star gets brighter. So this is what Paczyński proposed, that we just observe millions of stars and look for these which get brighter. Actually, this shape is kind of almost Gaussian, but it's called Paczyński curve. And typically, it lasts in our galaxy between weeks and months, sometimes years. So you look actually for any type of range of timescales you can essentially think of. It depends on the configuration and the mass and so on. Another flavor is because there are these 2 images, also the source changes its position. So this is what microlensing causes to the star. Instead of being here, it does some funny things. It actually moves away from its original position, and then it gradually comes back to the position. And here we're talking about the separations of milli-arcseconds, right? So milli-arc second is nothing you can observe with a regular telescope. Typically you get arc seconds, so you need to go 1,000 times more precise to measure this kind of phenomena. And for 30 years of microlensing, after Paczyński's idea, we've been only dealing with this part, right? So this was actually unachievable until recently, and I'll show you some exciting things we can do now. And just to mention about the idea of Paczyński, where actually microlensing started. So Paczyński proposed to look for these compact objects called MACHOs, massive astrophysical compact halo objects, essentially black holes, and look for lensing events towards larger Magellan clouds. So you have the halo filled with dark matter, and 50 kiloparsecs away, you have your sources, and you just look for microlensing events on these stars. So that was the original microlensing idea. And this is how the Polish project OGLE started. So this is the telescope built in 1996. It's actually very close, very similar to the one you have in Skinakas. So this is DFM, the yellow one, built there. And it's been operational since then. Actually, only interrupted for COVID for like a year or so, but it's still operating. So I spent some like 2 years in total, over 15 years traveling there by myself and observing in Chile. It was quite fun. So this is a dedicated project. It has only one goal, so to observe millions of stars as Paczynski proposed. However, the results here are actually the non-detection results. So with the OGLE data we studied, so we say that there's not enough these microlensing events to account for halo lenses. So essentially we can rule out at least fraction of the mass spectrum. So this is the mass of the black hole, and this is the density and the number density of these black holes in the halo. So with microlensing, with OGLE data, we can rule out this part of the mass spectrum. Everything below 100 solar masses there is no dark matter in our halo with compact objects below 100 solar masses. So essentially, after 40 years after Paczynski's idea, we can say no to his at least to this part of the mass spectrum. Okay, so the OGLE project is looking also in the very center of the galaxy. So this is the Milky Way. This is the center where most of the stars are. So this is where microlensing happens very often. So every year we see thousands of microlensing events, right? But they tell us nothing, essentially, because we can only tell that their microlensing happened. We don't know anything about the lens. We have no lens mass measurement. We have no lens distance measurement because of a lot of degeneracies happening in that curve. So we were trying to tackle this problem to look for some anomalies in the light curve. If you have the observer sitting on Earth going around the sun, then you start to introduce the parallax effect to microlensing, and this helps break, at least partially, the degeneracy. So we were able to find some candidates for dark lenses. You see, this is the probability density we found. So something between 2 and 10 solar masses. This is the length of this event here, for example. So there are some ways to go around it. You need to have very nice light curves, very dense ones, and detect these anomalies in the light curve. So then you can tell more about the lens itself, and you can narrow down your search for black holes among the lenses we see. What we achieved here is that we were able to say that maybe there is no mass gap. At least the lenses, dark lenses we found, that were covering the whole mass spectrum. So very crudely, but still we could tell that from microlensing we could feel the mass gap between neutron stars and black holes. Okay, so coming back to that figure, I will emphasize one event here, which is called OGLE 110462. So this is an event found, which was alerted by OGLE in 2011. You see its light curve. It's beautifully covered by multiple telescopes and multiple surveys. So it lasted something like a year or so. So you have very dense light curve coverage. And then on top of that, people with access to Hubble Space Telescope, they observed this very star for a couple of years. So you see one observation a year, and then what we were able to see, we were able to measure the displacement of the source position. So apart from this photometric change, we were able for the first time measure the astrometric time series, how the source moved on the sky due to lensing. And this combined together gave us the very first detection of a single black hole with mass about 8 solar masses at a distance of 1.5 kiloparsecs. But this was only possible if you have access to Hubble and you can observe all those thousands of events, right? So we after something like 20 years of hunting, we found one like this, because this is a very expensive approach. What we can do, we can use Gaia instead. And Gaia is essentially a Hubble for the whole sky. Just a few words about Gaia. This is actually, I brought Gaia for you here. So if you want to see how it flies, you can have a look. It's actually very much, I shrunk it to bring it to this room. Otherwise, it probably wouldn't fit here. It's 10 meters in diameter, actually. It's very big. So Gaia is a purely ESA mission, very European. So there is also a consortium for data processing, and there is. So it was launched in 2013, and now we know it's the very last couple of months actually it operates. It was actually meant to run until 2019, but there was enough of Russian fuel, so we could keep it running for 5 more years, thanks to Soyuz rocket it was launched with. Early 2025 is now the prediction it will stop operating. And the fuel is needed so that it can stay in the orbit where it is, and it can point where we want it. It doesn't move like Hubble. It essentially scans the whole sky, and it goes around the sun together with Earth. It's in L2, and its main goal is actually to measure the parallaxes. So measure the tiny displacements of stars due to parallax, so that we can measure distances to stars. It's 1.4 meter, the mirrors, there are 2 mirrors like this. It can go down to 20 and a half, and it monitors essentially the entire sky, which is 2 billion sources. And it's actually a very versatile instrument because it collects astrometry. Astrometry is the main goal, but also it collects photometry and spectroscopy for all these 2 billion sources in time domain. So you can imagine you have a movie of the entire sky for 10 years, where for each object you have not only the evolution of brightness, but also you have evolution of positions and spectroscopy. And this data is being made public by the consortium we are members of, and then the most recent Gaia data release number 3 was out in June 2022. It only contained a fraction of the data. Now the DR4 planned for 25, maybe early 26 actually, is going to contain everything, right? So the astronomical community will be swamped with lots of products. So there will be not only photometry, there will be astrometric time series, spectroscopy time series. You will have an SED for every star, not once, but hundreds of times, right? So in time domain. So this is going to be a game changer. It is already a game changer for many fields of astronomy, but with DR4 it's going to be a huge change. But what we are interested in, astrometry of microlensing events. This is what Gaia is actually built for, right? Essentially, Gaia measures positions. So if the object is essentially doing nothing, it has its proper motion and parallax, then it would move on the sky like the magenta curve, right? So it would just do this. However, if there is lensing involved, if you combine these two motions, then you have the motion on the sky will be somewhat distorted. And here you see the residuals between these two motions. So this is a simulation so far of the astrometric signal we expect from Gaia for 10 solar mass black hole at 2 kiloparsecs, right? So we already seen the data. It was not made public. It will become public in 2026. However, we can tell that the signal is there. Gaia can deliver this for microlensing events. So this is something what we currently work on for DR4. So I will tell you more probably in 2 years' time. Yes.
Just to understand, this is you have a 10 solar mass black hole which moves and restores the positions of stars close to the star.
But here you have essentially a star. This is the motion of the star if there was no lensing, the magenta line. And then and this star is moving. And then in front of the star, there is a black hole passing, right? So on top of the motion of the star, you have the distortion of the lensing. So both of them move, right?
But there are a lot of parameters because the motion of the black hole does not necessarily...
Yeah. So the motion of the black hole could be perpendicular, for example, right? So the shape of that deformation depends on this.
It will be different. Okay.
And you can measure this, actually. This signal is there already, right? So the main thing is that we observe the star, and the star can do some funny flips, and it means that there's been a black hole in front. So if you want to play with simulating Gaia data, there is a very nice tool designed by our friends in Cambridge. So Astromet is very nice. We use it for. The main advantage of Gaia, as I mentioned, is observing the whole sky, right? So not only the parts where there is most of microlensing events here, but also the disk, the halo. Essentially, Gaia looks everywhere. On top of Gaia collecting the data, and then we release it in releases, there is something what we established in Cambridge was called Gaia Science Alerts, and this is the website. So this has been the system which was looking for, was actually checking the daily yield of Gaia. Gaia was scanning the sky and delivering the data downlinked. The data was downlinked, and we were looking for anomalies in the data. So this is one of the anomalies. So the star is essentially bright. This is the brightness of the star over many years, and then suddenly it gets brighter, right? So we want to know about it. At the moment, it's getting brighter, because we might miss the opportunity to study it. So this is an example of microlensing event, of course, but you can think about the same principle for CVs, novae, tidal disruption events, supernovae, even our coronavirus type stars are of interest. So we've been doing a completely unbiased transient search over the last 10 years with Gaia. And in principle, we've been finding 1 to 5 new microlensing events every week, but also we were finding them all over the sky, both north, south, and anywhere you look, there were microlensing events. I'll just show a couple of examples of some results we have so far. This is one of our first events we found, but probably this was the most complex ever microlensing event found. So you see these large red dots, these are the Gaia observations. So what I want to emphasize here is that Gaia is busy scanning the entire sky, so it cannot spend a lot of time looking at in one direction, right? So it has to move on, right? So typically you get one observation every 30 days, or a couple of weeks, right? So we can find something. We found an anomaly here, but then Gaia moved on. But thanks to the alerting system, we knew that there is something weird going on. So this is where we found the alert, and then we started observing it with a network of telescopes. And in this particular case, there was 51 observatories involved. And we observed it for, you see all this data here, we observed it for 2 years. And we found it's been doing a crazy shape. This is the light curve of a microlensing event, but this is not a single microlensing event. This is a binary microlensing event, right? This is where you have the beautiful caustics, and when the source crosses the caustic, then you have these crazy jumps, many more parameters, but beautiful light curves. You see these caustics also in the swimming pool, right? I see them every morning in my swimming pool here. So it always reminds me about this event. So when you have this source crossing, it can get amplified quite a lot. So only thanks to this follow-up, we were able to essentially measure this system. Without seeing the lens, we were able to constrain all the parameters of the lens. It turns out it's not a black hole, unfortunately. It was just a boring binary system, if you care. But then it showed that we can do that. We can do it. We have a network which is able to respond, and then we can break the degeneracies in the data. And there was 20,000 observations collected for that very target. You would never get time on any telescope to get this kind of amount of data, right? And we got these 50 telescopes involved for free, right? We just asked nicely people to observe for us, and they all ended up as co-authors in the paper. There is another one happening it's finished recently, 23 ATS. Fairly recent one. So again, this is a binary microlensing event where you have the standard curve and then it's disrupted by something crazy. And only thanks to the follow-up, we were able to get these tiny features of the light curve. You see the changes here within 5 hours. This object dropped from 12 magnitude to 15th magnitude, right? So crazy. You need to have a system which is observing 24 hours a day to be able to cover these kind of things. So this is probably, again, not a black hole, but this is an extremely luminous lens. So not that exciting, but still we proved that we have beautiful data we can collect with the telescope system. More success we had with this event. It was found in 2019. This was highly magnified, just a standard event. We had an alert here, and we covered it very, very densely. You see, this is essentially a couple of days of observations. The timescales are of days here, and we collected 10,000 observations of that on that one source, and we found that this is a dark lens. I'm not saying black hole. I'm saying it's a dark lens. So we measured the mass of about 1.1 solar masses. So most likely it's a white dwarf, right? But if you want to feel exotic, you can tell it's a primordial black hole at 1 solar mass. Why not? We can't tell them apart. That's the downside of microlensing. But we measured the mass of a dark object, which you would never be able to do it otherwise. And then the last example here is actually, this is an actual black hole candidate we just published with my student Cornel Hovil. This was one of the longest events. So it lasted a couple of years. And we think the mass is about 12 solar masses at about a distance of 2 kiloparsecs. But we still have this near-far degeneracy. So if it's near, it's massive. If it's far, it's not that massive. But we hope this degeneracy will go away with the Gaia data in 2026. So this is one of the most exciting ones. However, here, as you see in the light curve, we didn't get that much of follow-up. This is because this was fairly early, and we didn't have many telescopes in that part of the sky. So this is kind of a bad example that the follow-up was not achieved for that particular event. Okay, moving on to some bigger things, just a couple of words about LSST, Vera Rubin Observatory. So this is how it's going to look. I have here that it will start operating in 2025, although you never know with LSST because it's always delayed. Hopefully it will start soon. Anyway, so it's going to be revolutionary in a sense that it's a very big, fast telescope with huge field of view and also huge depth. So going 25 magnitude survey, it's going to break the barriers we've been dealing with. So far we've been mostly reaching down to 20th magnitude in optical. This is going to be 25. Of course, this is going to be in Chile, so only half of the sky, right? But very, very deep. Looking from the microlensing perspective, there's going to be tens of thousands of events found by LSST, and among them, there's going to be hundreds of black holes, right? Now, we've been talking about single examples of potential black holes. With LSST, we go 2 orders of magnitude more. Essentially, we just probe deeper, we have more sources. So not, if you think 1 in a million is being lensed, and one in 1,000 of these 1 in a million is a black hole, then you can get your math. And you see how many black holes LSST is going to find. The problem is the astrometry, because there's no going to be Gaia for this. You need this astrometry component. But we're trying to figure out the cooperation with Gravity Plus. This is the VLTI interferometric instrument, which is now improving its sensitivity. So with that, you just need one observation. You don't need to follow it like HST or Gaia. You just need one observation, and then you actually see the images. This was done once, or actually twice, as a showcase, so we can break the degeneracy on that side. However, you still need the nice light curve. With LSST, again, it's not going to be to conduct very dense sampling, so we need to complement the light curves of LSST with photometric follow-up. So first we need to find an alert. LSST is going to flood us with alerts, but then we need to have the follow-up observations in terms of photometry. And the challenge here is that this is going to be very, very deep. So we need to go deep and dense and observe a lot of targets. So we have this network of telescopes built for Gaia, but we now would like to upgrade it so that this is also usable for LSST. So the challenge with LSST is essentially that there's going to be millions a day and tens of microlensing events, right? And very deep. Moreover, most of these microlensing events, they will come from the galactic plane. LSST was actually, whenever I talk with them, they are not even sure if they're going to observe the galactic plane because they're freaking out. This is going to be so dense and so many stars, so they might see nothing there. But I hope there's enough pressure so that they actually do observe it. So just to give you an impression, so this is the field of view of the LSST. This is the moon there, right? So in one shot, it's going to cover this part of the sky. So just to give you a comparison with something real, this is the Ogle image, 1.4 telescope, where the moon is actually filling the entire field of view. So Ogle is only this part of that LSST image. And then if you zoom in to this very tiny fraction there, you see there is loads of stars, right? And they kind of overlap with each other. So this is the main challenge for Ogle as well, but for LSST it's going to be an even larger challenge, the galactic plane. Okay, so now going to the telescope network. You might recognize this one here. I hope it's the right picture. We've established this for Gaia alerts in 2013 when we designed the alerting system in Cambridge, and we thought, okay, what's the point of alerting if no one is observing it? So this has been growing over years, and now we have telescopes essentially everywhere. It's been funded from multiple sources, and now the funding of optical radionet pilot is actually drying out, and we've just moved this to another program, which is called ACME, which is a joint program with particle physicists as well. So we're going to observe, essentially with this network, we're going to use it for time domain science in multi-messenger environment, right? So not only microlensing events, not only quasars, but also ice cube alerts or gravitational wave counterparts. So this network currently has about 100 telescopes, and they come in different sizes from 25 centimeters to 2.5 meters. Some of them are professional, some of them are amateur. We even have schools involved in the observations. Some outreach facilities these days, they can get nice instruments, and then very often the kids go and see the telescope in the afternoon, and then the telescope is just sitting there doing nothing in the night. So these are very nice facilities which recently are joining us. And there are manual telescopes, like the one we have near Warsaw. There are robotic telescopes, like this is the Liverpool telescope, for example, in La Palma. Some of them have good weather, some of them have poor weather. Some of them are essentially volunteering their observing time, but sometimes we need to write a proposal to ask for some time dedicated for that particular network. So you see this is a whole infrastructure involved. So to operate this infrastructure, we built something what we call Black Hole Target and Observational Manager, so BHTOM in short. And it was built together with Las Cumbres Observatory in California. This is Las Cumbres is a famous network of telescopes around the globe, and they operate them essentially as one observatory, and they make their software public, so they shared their software with us, and then on top of that we built our system. And actually the workshop we're going to have here in this very building next week, we'll have with people coming from California to here. So if you're interested, please see us and talk to us. We will be working on the actual code for that system over the next week. So what this tool does is essentially a web tool for coordination for time domain observations. It can handle automated observation requests. So if you have a target of interest, you can send it to the system. It processes the raw images from all these 100 telescopes. That's the thing. So you just upload your image and we do the measurements for you. It does the standardization, and it reaches to the archives of time domain as well. There's plenty of archives. You can learn a lot, so we do that as well. And it's open for new users. So if you're interested in one supernova, you want to observe it, and you don't have any proposal ongoing now, then you can send it to us and we can observe it for you. Or if you're interested in some long-term monitoring of a quasar or something like this, then also we can add it to the system, and we'll give you the data essentially for free, no proposals and no hassle. And of course, we are open to new telescopes. So I'm hoping that after this visit here, Skinnacas will be more present in that network. So I will show you some details about the system now. So this is a schema, how it operates. So there are surveys like Gaia, ZTF, Assassin, LSST in future. So they deliver alerts. The alerts are then going to brokers. Brokers are, there are a couple of brokers, Fink, Lazaire, Antares, and many more. This is the systems you can weed through all these flood of alerts. You can find your interests. If you're interested in supernovae, then you can find these handful of supernovae you're interested in. If you're interested in microlensing, then you can just search for microlensing events. So this gets to this is the job of the users. And these users, they come with multiple ideas, scientific ideas. For example, there are 10 candidates for gravitational wave optical counterparts, right? So someone was using the tools somewhere upstream to find, let's say, 10 candidates. But now we need to do something with them. Another type of request is that you want to observe this object found by Gaia for 1 year, right? You don't know what it's going to do, if it's going to last 1 year or 2 years, you don't know. You just want to keep observing it. So this kind of requests, they go to our system. And then the system is talking to the telescopes, the network of telescopes, which they observe whenever they can and whatever they can. So it's up to them sometimes to decide. Sometimes we suggest which targets should be observed. And then these telescopes deliver data back to us, right? You see, the data is not going back to the users, it's going back to us. What we also do, we query the archives, and then we combine it all to build science-ready data products. And this is what the users get. You see, so we try to keep the users away from the telescopes. I know it's horrible because every astronomer should be able to handle data, and astronomers should observe. However, these days it's not possible, right? You want to do your science and you're good at some things. You don't want to get your hands dirty with dealing with proposals, applications, data processing, and so on. So we do it everything. We can do everything for you, and you get the data which is ready, and then you can sit down and write your paper. Of course, all this these days has to be robotized, so you can replace these humans with bots, and essentially the entire flow can operate without any human intervention. Of course, ideally, right? Nothing is ideal, but that's the principle. This is where we should be getting, so that we can just sit and see robots writing our papers. Okay, so as I said, we deal with multiple science cases. Anything what is changing, not only photometrically, but also in spectroscopy, astrometry, polarimetry. This is what we want to have in our system. So you see examples of cataclysmic variables, microlensing events, some flares in quasars, or some AGNs doing some crazy stuff. So anything time domain is valid for our case. And here are some papers we wrote. Some of them are, of course, on microlensing, because this is where we come in. But also there is a large Hungarian group we work with, and they write papers on young stellar objects. There are papers on supernovae. There's a planet we found, and stuff like this. So to show some examples about the core what we do, as I mentioned, we do the automated data processing. So these are the images collected by some of our telescopes. Some of them are small telescopes, some of them are larger telescopes, and then we get this data and we measure all the stars from every image, right? And then we do the standardization. And there's an automated standardization, so we can figure out which filter you've been using, and we can find the best matching filter. So the data gets standardized using Gaia catalog. And then the object of interest is being measured, and the photometry is being stored, and everything can be downloaded for everyone who is registered in the system. Here are some examples of details of these light curves. This is a famous nearby supernova. So you see, these are the light curves where you actually don't see the differences between the telescopes, right? So each of these data points is collected with different telescope. So we try to minimize the differences between them. And in this example, again, you see the light curve, multiple filters. These are the filters we observe with. However, you don't see the differences between different instruments anymore. And here, this tiny anomaly there is due to a planet. So this is the first planet Gaia actually found using the data we got with the follow-up. So here's another example of a target, very recent target we've been observing. And here you also see a gallery of some of the telescopes we work with. So this is actually a Belgian amateur observatory. They collect lots of data. And these are other telescopes in different places in the world. So here is, again, is the light curve of a crazy microlensing event with some bumps here and there. It was extremely bright, almost naked eye. And here I just wanted to emphasize that here we have data from CMOS cameras. And these are already thousands of images we've collected over the last couple of days. From Rode Observatory, which is in Chile, is essentially purely amateur observatory. And then also with Las Cumbres Observatory, and they actually use the same camera. So we already have some training sets to think of and to work on. I think this would be a good example of this data set. As I said, we have thousands of observations for that particular target with various instruments. Some statistics here. So this is the statistics of data uploads over last year. So the quarter of it actually comes from this one amateur observer who's a very observing. This is a retired physics professor who has more Nature papers than anyone else. So you can actually employ him and boost your institute's rankings. Because he essentially has this telescope, robotic telescopes, which delivers a lot of data. The data is not perfect, I must admit, but still it's a lot of data, and it has a lot of scientific value. Then we work with Las Cumbres Observatory a lot, so that's why we have a lot of data. But what I wanted to show is that apart from these two observatories, then the rest of it, there's 70 observatories, which has been active in last year more actively. So half of our data actually comes from a very heterogeneous network of telescopes. And if we only use these two, we will only get half of the data we want. And of course, we're trying to encourage all these people to collect more and more observations. But the thing is that we can process it all. And I hope that Skinakas will appear here as well at some point. And now we process something like 5,000 images every week. But at this moment, we can process many more. One word about the archives. This is an example of NADA's famous quasar, which actually got brighter and then it's now fading below it used to be, so no one knows what's going on. And that's why NADA is still trying to finish her thesis. But anyway, we read optical data sets, we read radio, we read near-infrared. So you can have, for free, you can essentially have 20 years of light curve for your object of interest. So that's a nice feature of the system you can explore. And of course, everything is, as I said, everything is API'd. So all functionalities are accessible via API, and you can write your scripts. And we provide scripts as well for data download, for data upload, for target selection, and everything can be scripted. There is one system called Astrophysics we work with, and they already have a button where you press add this target for observation of BHDOM. So this is actually a growing feature of BHDOM. So some of the challenges to the end, I will mention that we face here a growing number of telescopes, which is good and bad at the same time, because it's challenging to handle them, and then the number of data points to process is growing. As I mentioned, we have these amateur telescopes involved, so they have great potential. They require training, and it costs us some time and effort, but it's worth it, definitely. But quite often they deliver poor data, so that data could be helped with also on the astronomical side we can help them improve the data quality, but also we can probably improve the data once it's delivered to us. The angular resolution of the images, this is something what is bothering us the most, I think, I would say. And I say, as I showed this ogle image here, right? And there are some Gaia points marked there. So Gaia can resolve things which are unresolved from the ground, but ogle is actually not such a bad position because it has a good seeing. Most of our telescopes are very seeing limited, and I'm saying about 3 arc seconds. So everything is blurred to 3 arc seconds, or maybe more. So these images have less value because of that blending and varying conditions. However, in principle, we know what we are looking at, right? We have Gaia, we have the whole sky monitored by Gaia already. We have PS1, we have decaps. So you see this is the image of more or less the same field here with decaps, which goes much deeper than ogle or even Gaia. So in principle, we have the prior knowledge of what we are looking at, but we are not using it at all. We treat every single image as a new system, and we try to discover things which are changing their brightness. Most of the things, they don't change their brightness, but this is something what could be worked on. Growing number of images, that's another challenge. So at the moment, we spend 1 minute per image. It's extremely slow, but this is something what we will be working on with the distributed networking of processing units. That's at least the approach we want to make. And of course, one thing we do, and we are now expanding on, is that if we observe one star, we also observe the thousands of objects in the same field of view, right? So if this is our star of interest, then all the other stars are also being observed. So serendipitously, we also build a history of all these objects in the vicinity of our target. So we already have this vast database, and there are millions of data points already collected, which could be extremely useful if you want to find, for example, the archival gravitational wave counterparts. And as I said, we go to the galactic plane mostly, where no one cares to looking, right? So some of the gravitational wave counterparts, for example, are missed because no one is looking into the galactic plane, and we do, and we have that data. So that could be searched for. So this is something that we are also working on. And of course, human resources. This is a challenge everyone faces. My last slides are the advertisements of the workshops we do. So we maintain this network running. First, it started in 2010 in Cambridge. It was all focused about Gaia and Gaia alerts. As I said, we started the network because of Gaia alerts. But then we moved to generically to time domain aspect, and we had one meeting already here. We enjoyed it very much. So that's why we have the meeting again in forthcoming weeks in here. It will be the 15th already, and it will be the celebrations of the 10th anniversary of Gaia alerts. So everything is recorded. You can watch it. You can join us. Actually, we will be in Forth for that meeting, but it will be all streamed and can be observed. So just to go quickly through the summary, black holes are hard to find. We need them to understand stellar evolution, dark matter, and physics. Single black holes are even harder to find. That's why we use microlensing for it. Precise photometry and astrometry are the key ingredients. And Gaia delivers astrometry, but we need the telescope network for the photometry. That's why we created that network. And LSST, it will be a challenge because there will be thousands of microlensing events, and we need light curves for them. The network of BHDOM has 100 telescopes worldwide, thousands of images, millions of data points. And the main challenge is how to improve the use of small telescopes to match the needs of the modern time domain astronomy. I stop here, just leaving you with the animation of events.
Thank you very much, Lucas. Any questions?
Great. Thank you. Great presentation and great topic indeed. I mean, from computer science even more. So I wonder if you can give us some insights as to the type of alerting system that is being done. So is it like manual? Is it automatic? Is it based on some known assumptions? And then with respect to the, at least for this part of the system, that the distributed network of the telescopes, the processing system that you have now, the capabilities, I mean, it's like, you have a couple of GPUs and that's that, or like we need massive star, or it takes a lot of energy? I mean,
well, so these are like two separate things.
Yes.
So the alerting systems, the one we have built in Cambridge, we started doing it like 15 years ago. So the technology was very different back then. So we had to make it extremely efficient because there were millions of data points coming, and we didn't have many computing resources. So actually now, after 10 years, we see that it's actually choking. The database is so big that we actually have to close it down sometimes because we are not able to process the data before the next chunk of data arrives, right? But only after 10 years, because it was only designed to last 5 years. So that's our experience with the alerting system. I also did an alerting system for the Ogle project, where the data is coming automatically. But automatization is the key. Otherwise, you will never be able to do that. In the Gaia alerts, there is an aspect of human eyeballing of the outcome, because we don't trust fully the very final outcome. But these are very small numbers. I'm talking about a few dozens of things a day, and we have a group of people who are actually eyeballing through it, right? Many other surveys and LSST in principle, they will just flood us with everything. It will be automated, but they don't care. They will not care about this is real, this is not real, deal with it, right? That's why people are building all these brokers to handle this. So this is what we kind of leave behind. And in our system, we tend to focus on particular targets. And in order to process it, we need some computing power, of course. So far, so it's a web system, but we run it in the cloud. I thought, I don't want to deal with the hardware issues on top of everything, right? So essentially, we hired a company who is purchasing some cloud space somewhere, right? It has its downsides because, for example, disk space is limited. A few days ago, we actually filled the whole disk and we have to stop it because half a tera was not enough to handle with the data flux. So these are the issues. We're not using GPUs at all because we're using some kind of traditional methods for data processing, imaging processing. They were not designed for GPUs, right? But we use the Dockerization, for example. So the actual package for data processing is going to be sealed in a Docker. So it means we can then distribute it over multiple nodes if we need this, right? So this is something what soon will be in place. And then we can handle way more requests of data processing. Very good answers.
yeah, thank you.
What's the reason that the lens signal is 6 times more luminous than the raw image? So 6 means a bit strange, not 2 times, not
yeah. So the shape of the microlensing curve can reveal actually that there is additional light. So if you have the background source star, and if this is lensed by a black hole, then you see this flux being amplified, right? And then the amount of amplification only depends on, it's just geometric, so it doesn't tell us anything. But if the lens is luminous, right, there is also light coming from here. It's not being lensed, right? So it's a constant flux, which is adding to the flux of this getting brighter. And we can measure it. We can see it in the shape of the light curve. This is another feature. It gives an offset, but if you then turn all the fluxes into magnitudes and so on, and it's all blended together, then you see suddenly that the total flux is actually sum of these two, and then only a fraction of it is getting brighter, right? Not all of it, right? Because this one stays. This is flux. So this is another nice feature of microlensing, that you can, if you have well-sampled light curve, you can measure the amount of light you get from the source and the lens. And in that way, you can disentangle black holes from stars. And the example I showed, that we could actually measure the ratio of the light. So we could tell that the lens is 6 times more luminous than the source. So we know that's definitely not a black hole, right?
Lukasz, very nice talk, thank you. This is a very interesting slide, and it shows the blips, but they are all in the galaxy. We don't have any in the halo, and I was wondering, that's probably extremely hard to see something like that. You have to see a star in another galaxy, and therefore you must have a dedicated telescope looking at a particular galaxy, which resolves all the stars there.
Yes, yes, you're right. Well, there was one there. This one here.
Yes.
You missed it.
Okay.
Yeah. Yes, so that was the original Paczynski idea, to look at this star. This is the external galaxy, right? Just observe this, and then you probe the halo.
Yes.
Right? And this experiment failed in a way because we proved that there is not enough lenses. However, with Gaia, for the first time, we can probe the entire sky, right? So we look into multiple directions. And for example, what we see a lot of events here, right? This is the anti-center of the Milky Way. You don't expect many events there. Why? Why there is many more events? Maybe there is an overpopulation of black holes in that direction, right? So we can still do something interesting. If you want to study the halo, then Gaia also gives you that. And I have some ideas I didn't mention here, how to do that. You can use, for example, quasars, sources, because they're everywhere. They are far away. So they allow you to probe a lot of line of sight. So this is what you can use Gaia for as well. But it's not on this animation.
You said that Gaia will die next year.
It will die, it will stop observing. But
It will stop observing.
it will stop observing, but the data will become public only in 26. So there is still a lot to come from Gaia, even though it stops observing, because it takes a lot of time to process all this data.
Maybe I'll ask a question. You mentioned that the Oakley experiment put an upper limit in the sense of the number of potential candidates for dark matter in the mass, but you said you exclude, if I noticed it correctly, black holes below 100 solar masses.
Below 100, yeah.
But is this because you have a mass function, so you would expect to have much more there and you don't have enough? That's the reason.
Yeah, we have essentially zero detections. So then, knowing the experiment, we can rule out if there was a black hole with mass of 100 solar masses in the halo, we should be able to see it, right, easily, because we have 20 years of data, right? But because we don't, then we place a conservative limit to that. And then beyond 100 solar masses, then we cannot exclude that so firmly. So there is still a tiny chance on that mass end.
If you have fewer, more massive black holes.
Yes, this is what Ogle cannot yet rule out because it's too short experiment. It's also focusing only on this part of the sky. Right?
I also have a question. So for your PhD program, you said that users are encouraged also to do some inside requests. Then I suppose you have some pack to evaluate. So who evaluated this? Because you said we send it to observer, but I suppose you cannot send all crazy requests, right?
Well,
you need to have somebody judge it.
Yeah, it's me. Well, we haven't established it at all. I wanted to avoid it as long as possible. We're still small, let's say, right? And we can handle it, let's say, manually. And I haven't seen anything crazy, and I'm open to people suggesting crazy ideas, right? And in that sense, if we grow, then maybe something like a tag would be necessary. And maybe there will be some requirements from the European Commission, who is sponsoring us as well, to have something like this. As long as I can, I will fight this to make it as simple as possible, right? If there's tag, then you have to start having proposals, then the reviewers. This is not where we want to be, right? So if you have any targets, just send them there. I don't even have to know about this. It just gets into the system, and it gets observed.
Okay, if there are no more questions, let's then do this again. This is 2:07.